Okay, so in the last lecture, we started discussing the relational algebra, right? Relational algebra. So, relational algebra is a central component of the relational model, and it offers certain operators which operate on relational instances and produce relational instances. And then we talked about two important two unary operators, the select and project operators. Okay, a couple of important points before I move on to other algebra operators. See, one of the common mistakes that people do when they are in the early stages of learning is put some in the condition here in a typical algebraic expression in the selection condition, they try to put another selection condition because they think that other selection condition produces a value or something like that. So, that will be an error. Okay. So, for example, let us just consider in this particular data there is only one Mahesh or whatever. Let us say that this particular result produces only one name. Okay. Let us consider the case that this result produces only one name. Even so, even if it produces just one name, it is important to recognize that what it produces is a relation, right. Even if it produces just a single value, it is actually a relation which has one column and one row and one value. It is still a relation. It is not to be confused with just the value. Okay. So, if this confusion is removed, then you will not have the tendency to kind of treat it as though it is a value and then try and put it in the condition here. So, the condition syntax is very fixed, I mean very much to be we discussed this condition syntax for this particular selection condition. It can only involve atomic operators that have attribute names and comparison operators with values or other attribute names, right. So, that is the atomic kind of thing. So, you cannot try and put another selection condition, equal to sigma something you cannot write here, for example. Okay. So, these are the certain. So, this point about even though the algebra expression produces a relation with single column and a single row, it is still a relation, that is to be clearly understood. It is not to be confused with the value that is present inside that. Okay. Now, with these points, let us proceed to understand what are the binary operators that are present in relational algebra. One of the first things that comes to our mind is that since relations are sets of tuples, what about set operations? The familiar set operations, will they be useful for us? The familiar set operations are the union, intersection and difference, right. These are the set operations, but how can we make use of these set operations? One issue that we find here in these relations is that each of these relation instances has a different number of attributes. See, one relation may have 3 attributes, the other relation may have 5 attributes, right. So, in one relation the tuples are of length 3 in the other relation the tuples are of length 5. So, it is not obvious how you can take simply union of those two things, because if you take such a union, then the very concept of producing a relation does not anymore work. Then the union will be union of 3 tuples and 5 tuples. So, it is not a relation instance, it is just some union, right. It is not of use for us. We want our algebra operations to produce relations, take relations and produce relations. So, it is kind of required that we must put some kind of condition before we can make use of these operators, the union, difference and intersection operators. So, that condition is what is called union compatibility. We call this condition as a union compatibility. So, basically we are just checking whether two relations are compatible for applying these union, difference and intersection operations. So, what is the compatibility that we are asking for? It is basically that the number of attributes in, so let us consider these two relations R1 with A1 through AK, R2 with B1 through Bm attributes. So, union compatibility basically says that the K should be equal to M, that means there should be equal number of attributes in both relations, and not only that, the domains of corresponding attributes should be same. So, the domain of AI should be domain of A1 should be equal to domain of B1, domain of A2 should be equal to the domain of B2, etc. So, if you want to combine take a union of tuples from R1 and R2, these attribute names may not matter, but the underlying values should come from the same set. If you take if you take a tuple and consider its first value, suppose this is integer and if this is string, then the union does not work out that well, right. So, you want both first tuple to be integer in both these relations and so on. So, you want domain of corresponding attributes to be the same and the number of attributes should itself be same. So, under these two circumstances conditions, if these two conditions are satisfied, then we will call that pair of relations as union compatible, and then we can talk about producing unions and differences and all that. Okay. So, set operations union, intersection, difference, these are applicable to relations if two relations if their schemes are union compatible, otherwise we will not be able to apply union, intersection and difference in our context, because our operators are relational algebra operators. We want them to take relations and then produce relations. So, another issue that comes up is supposing R3 is equal to R1 union R2, where R1 R2 are union compatible and we are producing. So, what should be the schema for R3? Should it be, let us say, the schema of R1 or should it be the schema of R2, right. So, that question comes up. So, what we do is we just simply follow a convention saying that the left operators operands, left operands schema is what we take as the schema of the result operation. Okay. See, notice that these schemas are compatible, but the attribute names may be different. So, one set of attribute names we have to take, which set is to be decided. So, what we do is follow a convention saying that the first operand's schema is what we use for the result. Okay. Is that point clear? So, just as a convention. Okay. Now, let us look at some examples of application of this union operators. Okay. The definitions are very simple. So, R1, R2 are relation schemes with capital R1, capital R2, and R2 is union compatible with R1, then the operators are defined like this: R1 union R2 is the set of all tuples T such that T either belongs to R1 or belongs to R2. Take the tuples that belong to either one of them and then simply take the whole set together. So, it is possible that some tuple exists both in R1 as well as in R2, in which case obviously only one instance, because it is a set, right, it should not contain duplicates. So, only one tuple will exist. Now, the intersection is defined in a similar way, in the usual way. So, R1 intersection R2 is the set of all tuples that belong to both R1 as well as R2, and R1 difference R2 is the set of all tuples that belong to R1 and do not belong to R2. So, these are the usual definitions of union, intersection and difference. So, and by convention in all these cases the scheme of the result. So, this is the result relation, right. So, is the scheme of the first operand, that is R1. Okay. Now, let us look at another. So, I am actually skipping giving specific examples for this R1, because these are very familiar operators for us, the union, intersection and difference. We will see that coming up later in other examples. Okay. Now, moving further, we oftentimes actually want to combine information from one relation with information in other relation, irrespective of whether they are actually union compatible or otherwise. Sometimes we need to do that, whereas the union allows us to combine information from one relation to and another relation, provided they are union compatible, right. But even if when they are not union compatible also, we would like to combine, but the different kind of a combination is that actually I want to take a tuple from here and concatenate the tuple from the other relation. Right now what we are doing is taking tuples from one relation and taking tuples from the other relation and then simply adding them together into one long list. But instead, let us say I want to take one tuple from here, take another tuple from there and then concatenate the tuples and produce a new tuple. Sometimes I may need that. So, we will see an operator that actually allows us to do that. And this is also very familiar operator for us, actually, the cross product of sets. The cross product of sets, we will recall the definition of a cross product. So, in the context of relations, let us look at this carefully now. R1 is a relation on the schema A1 through AM, okay, and it has certain S number of tuples. So, I have written as A11, 12, 1M. So, all the first tuple has the first subscript as 1, the second tuple has the first subscript as 2 and then the remaining things as 1, 2, 3 up to M, and the last tuple is AS1, AS2. So, there are S number of tuples in the first relation. In a similar way, R2 has B1 through Bn, n number of attributes, and it has some T number of tuples. So, S and T. So, R1 has S tuples, R2 has T tuples, and so we will now define this cross product. The cross product of R1 cross R2, R1 R2 denoted as R1, with this symbol cross R2 is this relation. Okay. So, what is this relation? The schema of this relation is the concatenation of the schema of this and the schema of that. So, A1 through Am and B1 through Bn, all attributes are present. And what we do is, you might actually wonder what is this guy doing. Well, this is going to produce huge amount of data. Suppose this relation has 1000 tuples and this relation has another 1000 tuples, then you are going to produce a million tuples in the output. Well, is it really useful? Yes, we will see that. We will come to that point a little later. So, what it basically does is to combine this tuple with every tuple here and produce a tuple here, this operator. So, A11, A12, A1m is combining with B11, B12, Bn1n and also B21, B22, I mean this second tuple and the tth tuple, like that. So, it produces, this produces some t number of tuples, this produces t number of tuples, etc. You will get so many number of tuples. So, the operator itself is clear, but then we might actually wonder how useful is this operator is going to be, because it is going to actually produce a huge amount of data. Okay. So, let us look at an example situation where we will need this cross product, but then we also will notice how exactly the cross product is going to be used in data retrieval queries. Okay. So, obtain the list of professors ID and name along with the name of their respective departments. Okay. Here is the data retrieval query request or query. Obtain the list of professors ID and name of the professor along with the name of their respective departments. Okay. So, where is this information? Just I want you to look at your schema diagram and then tell me where what are all the relations in which this particular information is present. Is it just there in the professor relation itself? In the professor relation, do we have the name of the departments? We do not have the name of the department. We have the name of the department inside in another relation, which is the department relation. And there is a foreign key in professor that refers to department relations, and so you need to actually combine this information and then obtain the name of the department. So, info is present, the required information is present in two relations, the professor and the department. If you want, we can go back to the schema and have a look at it, but I suppose you have the schema with you, but let me try whether this works. I mean, we will have to apparently go to the pen and there we are. So, if you just want to have a look at the relation scheme, we have it here. So, you can see that professor has name and department number alone. So, if you want to know the name of the department, it is present in the department table. So, that is why we need to combine these two things, and so and you can see that these are different relations, and so there is no question of taking any union or anything like that. It does not work that way. So, how it works is that I should consider a cross product of these two things. That is the only way I can combine information from this to that. I can take a tuple from here and then concatenate the tuple from there and then see what best I can do with that. You can see that issue. So, that is where the cross product, but you also see that we are doing unnecessary work, because we are combining a professor with all 13 departments, 14 departments, whatever, which are actually unnecessary. Okay, so now let us proceed. So, I will now kind of solve this. Let us see how we can do that. So, let me project another thing is that okay. So, let me illustrate several points that come up here with this thing notation also. So, we are taking the professor table, I mean relation, sorry, and then projecting employee ID, name and department number, because these are the only things that were relevant for us right now in this particular query. We want name, ID and name and department number of from the professor. So, let us so this particular thing where I on the left hand side I give a new relation name and then give a bunch of exactly the same number of attributes as I am projecting here is an important construct. This is called the renaming of attributes. We are renaming the attributes like this. So, this particular operator, the project operator basically takes the employee ID name and department number of professor relation and projects them out, right, and discards the rest of the attributes. So, it produces a subtuple. For every tuple it produces the subtuple consisting of only these component values from these components, values from these attributes, right. So, you get, since it contains the employee ID which is a key for professor, you will get as many tuples as there are in the professor relation. Okay. So, you get all of them, but only thing is here I am renaming them like this. We will see why exactly we do that, but there I want to illustrate, I want to exactly define the process of renaming. Okay. So, we put a new relation name here and give new or even sometimes the same names, and then use this operator. This operator is can be thought of as assignment operator. Assignment operator in my view should be always an asymmetric operator. It should not be looking symmetric like equal to and things like that. So, I use this arrow like this to say that this result will be assigned to this new relation, and in the process the attributes will be renamed as these attributes. Okay. So, that is what we are having. In some textbooks they also introduce a new they introduce an operator for doing this. It is called a row operator, okay, and they use that. But instead we will follow this convention in our slides, that whenever we want to rename we will, and also this kind of this relation stands for some kind of an intermediate result in our formulation of the solution for this query. So, okay, let us proceed and then I will come back to this if necessary. So, and in a similar way I am producing a new relation called department detail, and there where since I am interested in the name of the departments, so I am projecting department ID and name from the department relation and renaming them as DID and DName. So, the name is getting renamed as DName here. The names of these attributes are important, so remember that. So, the name is getting replaced by DName, and then we have a now we can, now that we got the relevant information from both professor and department, we can actually combine them and produce a new relation called prof department using the cross product. Okay. So, once we do this, we have tuples from this and tuples from this concatenated. So, a tuple from this will get concatenated with every tuple from the other relation, and we have the bunch of tuples. Obviously, we are not interested in all those combinations. We are interested in meaningful combinations of this particular cross product. What are meaningful combinations in this case? In this case, for a combination to be meaningful, I mean a tuple concatenated with another tuple here, for it to be meaningful in our context, what is the condition it should satisfy? Both of them should refer to the same department, right. If I take a professor from computer science department and then take a mechanical engineering department tuple and then simply combine, that is not going to be useful for me at all, right. So, for this combination of tuples from this to this to be useful, we would like both the tuples to refer to the same department. And how do we ensure that? That is simple, because we have the department number here and department ID here. So, we can impose a condition saying that they should be equal to each other. If we impose that condition, then we will get meaningful combinations of these tuples. So, that is what we will do immediately. So, desired professor department tuples are those. So, we can now use the selection operator to get the appropriate combinations. So, department number equals DID. So, department number exists in the in this particular yeah. So, what is the scheme of this prof department? Scheme of the prof department is EID P name department number DID D name, the concatenation of these two schemes. And so, in that scheme these are both attributes, and that is why I had to do the renaming, because if I do not do the renaming, this name attribute is common to both the relations, right. So, if you combine the information from this and this, then we should ensure that the attribute names are different, right. So, you cannot have the same attribute name occurring two times in a relation scheme, that is not allowed. So, we did the appropriate rename, we called it P name here and then we called it D name here. So, that when you take the concatenation of these schemas, we get a proper schema, and then now we are applying the selection operator to get to impose this condition to, so that we get meaningful combinations of tuples from the cross product. So, this particular phenomenon of taking the cross product of two relations and selecting the required combinations occurs very often, occurs almost always. This is the case where we will use the cross product, and so there is a strong motivation to actually combine these two kind of things into one operator. So, we will see that actually in a short while now. Okay. Now, finally, to get the result of this particular obtain the list of professors along with the name of their respective departments, all that we have to now do is to take this desired professor department, project EID, P name and D name, right. So, is that clear as to how we have done the now notice one thing, that if you have the operator for the let me try okay, first let me take any questions on this. Is this clear? Do you want me to go over this again? Is this clear? First thing is we are renaming the we are projecting desired attributes from professor and renaming them and then getting an intermediate relation called professor detail, and then we are taking relevant attributes from department and projecting the relevant attributes from department and then producing a intermediate relation called department detail with these two names, and then we are doing a cross product. And since the cross product produces a lot of combinations of tuples which are not really meaningful, we are going to impose this condition that department number should be equal to department ID, and only such combinations are meaningful for us, and we are calling that as desired professor department, and then from there we are projecting whatever the attributes that we actually require, the EID, PName and DName. That is how we will get the result. Now, this style of writing a query is kind of desirable, because first thing is that we are able to organize our thinking and then produce some meaningful names for the intermediate relations. These are the intermediate relations, and we are giving some meaningful names for those intermediate relations, and then finally producing one relation, one relational algebra expression. Okay. Supposing we adopt that particular operator called the rename operator. Okay. If we have the rename operator, how exactly this gets written, I will show you. Let us see, let me try and write that. Okay. So, the rename operator is called the row operator, okay. And then whatever is the new names we should write here. Okay. What are those new names? EID, PName and department number. EID, PName and department number. Now, so what is written inside is basically this entire expression, pi employee ID, name, department number, professor. So, you can imagine that being written here, pi the employee ID, name and department number, this and then we can have professor. Is there a way to move this? Okay. So, you can imagine this kind of a situation. So, this stands for this relation now. That expression that I wrote there with this row operator stands for this particular relation, prof detail. So, we did not name it as prof detail. Okay. Instead, what we did is to simply produce it as a expression. Now, this is a rename operator. So, what it takes is takes a relation and then renames the attributes like this, and then gives a new relation. Okay. So, what we did in this slide, in the actual the slide that I was showing, is to kind of name this entire relation as prof detail. Okay. So, it is an intermediate thing. In a similar way, you can assume, you can see that I will produce this department detail in a similar way by using a row operator, row DID DName of this particular thing, then that will give you another the intermediate relation. Then I can do a cross product and so on. So, I can basically take this and then do a cross product and then give that other thing that we had, DID DName from, okay, we have pi here and so on. The point I am trying to illustrate here is that we have, so inside this there is a pi expression, projection expression, and here is the rename operator, and now we can see that this is the cross product, okay, the entire cross product. Now, after the cross product, we basically did the selection operator, selection on that cross product. Okay. So, we can imagine that this entire thing is inside like this, and then put a selection with the selection condition, department number equals DID, and then and then actually as a final step we are taking this entire thing and then producing and then finally giving a pi with EID E name, EID P name and D name. Okay. So, this is actually the relational algebra expression that produces that gives us the result for this particular query, obtain the list of professors along with the name of their respective departments. Okay. Are you getting the point that this entire thing in fact can actually be expressed as one single expression like this, which has inside this is the cross product, this entire cross product thing. Okay, let's not bother about that. So basically pen color I can choose, I think, right. So this is the entire cross product expression. So I can put that here and then apply the selection and then finally do the projection. So I get an expression, but as you can see this big expression is kind of difficult to understand. So it is a good style to write the expression in this way, where we give meaningful names for the intermediate relations, okay, and then combine and then use so many steps to kind of finally produce the result that we want. Okay. So I want you to follow this kind of style of writing where we put sub expressions on the right hand side, assign it to meaningful intermediate relations with appropriate naming for the attributes if necessary, and then combine them and then use one line for each of the operators that we are producing, we are requiring to use, and then finally produce the result. So it's kind of easy for us for you to develop and then understand the query, and it's also easy for anybody who is looking at this query and understand that yes, the query is really producing exactly the kind of result we want. Okay. So even though theoretically you can express the entire thing as one big relational algebra expression like this with the help of the row operator. The row operator I did not introduce formally, but there is a row operator which basically does the renaming. Okay. So are there any questions now in this particular thing? So we illustrated several points here of renaming and then giving meaningful names for intermediate relations and then making use of those intermediate relations on the right hand side again and produce new relations and then finally produce the result that we want. So with that, let me see whether I can take you a little further. Okay. The other point that we notice here is that after the cross product in general produces huge number of tuples and lot of combinations of tuples from one operator, one operand and the other operand, and it is generally seen that it is that all the combinations are not meaningful, and so we most often follow it up by having a selection operator. And since the combination of cross product followed by selection is such an often occurring phenomenon, what we will actually do is to introduce a new operator, and that operator is actually you would have heard about it, it is the join operator, the join operator. So we will discuss the join operators and the various variations of join operators in the next lecture.